Hello viewers, today we will discuss saturation flow at signal control intersections. Assume that at an intersection approach signal were to stay green for an entire 1 hour and there is a dense platoon of vehicle behind the stop line. Then the number of vehicles that would pass through the intersection from this approach will be the saturation flow rate. The condition is that there should be a continuous queue of vehicles behind the stop line and the green time available to the approach or to the movement is for 1 hour. So saturation flow is the equivalent hourly rate at which vehicles can traverse an intersection approach under prevailing conditions in vehicles per hour of green or vehicles per hour of green per lane, assuming the green signal is available at all times and no lost times are experienced. So that is how the saturation flow is defined. It is expressed in units of vehicles per hour of green or vehicles per hour of green per lane. Generally, the saturation flow is independent of traffic and control factors. So there are two important terms. One is discharge rate and another is effective green time. Effective green time is the time during a given phase that is effectively available to permitted movement. So this can be very easily explained through this diagram. On x-axis you have the time and on y-axis you have rate of discharge of the queue in vehicles per hour. Now when traffic light turns to green, it takes some time to react to the change in signal and also to start the vehicle and accelerate, and therefore the headway for first few vehicles is relatively larger, means the flow at stop line is low. Gradually it builds up and then it reaches to the maximum point here. Then as long as the green time is available and Q is available, then the rate of discharge will be the maximum. After termination of the green time, start of the amber time, it again falls because some vehicle decide to continue and some drivers stop, and before start of the red this must be 0. Now this curve, blue one, this curve is the ideal curve for explaining saturation flow and green time. Now it is always convenient to replace this curve by a rectangle having the same area as the area under the blue line and the same height as the height of this graph, and this rectangle, you see dotted rectangle here, then the base of this rectangle is called effective green time, that is effectively available for discharge of the queue, and this time here is called start loss time and this is the end loss time here. So effective green time is green time plus amber time minus loss time, and loss time can be start loss time plus end loss time. Start loss time is the time interval between the commencement of the green and commencement of effective green, and end loss time is the time interval between the termination of the effective green and termination of the amber time or start of the red phase. What I showed you here in this graph is a situation where you have a long queue of vehicles and entire green time is utilized. But there can be situation where the queue is not long enough and initially the flow is maximum and then it drops. So here this is operation at saturation flow rate and this is not the operation at maximum flow rate. This is start time again, start loss time, and this is the end loss time. Now here we should understand the difference between the flow and the capacity. Now this shaded area here, when you have the shaded area, that is the capacity, means when you fully utilize the green time, whereas this hatched area is the volume that has discharged from the stop line. So this volume is less than capacity because the queue was not long enough to utilize the entire green time. Saturation flow is given by this equation. If you know the number of vehicles that have cleared the intersection during effective green time, then calculate S is equal to N upon GE into 3600, where N number of vehicles crossing the stop line during effective green time and G is the effective green time. So it is expressed for per hour of green. Now this determination of saturation flow can be a somewhat complicated matter. It depends on roadway and traffic conditions, which can vary substantially from one region to another region. And factors which affect saturation flow are generally four: type or position of the lane, whether it is a near side lane or non-near side lane. Type basically means whether it is exclusive lane or non-exclusive lane. Then width of the lane, the gradient in the approach, and radius of turning movement for left turners and right turners. There are three methods generally used for estimation of saturation flow: UK method, US highway capacity manual method, and Indo highway capacity manual method. I will explain these three methods in this presentation. Now UK method is based on individual lanes, and the saturation flow is affected by the position of the lane and turning traffic. It says that straight through saturation flow for a non-near side lane of average width of 3.25 meter is 2080 PCU per hour, and for near side lane it is 1940 PCU per hour. The saturation flow decreases by 2% for every 1% uphill gradient, whereas there is no change in saturation flow on downhill grades. The effect of lane width is considered like this, that saturation flow increases or decreases by 100 PCU per hour per meter width of the lane. The standard lane width is taken as 3.25 meter, and if the lane width is less than or more than 3.25 meter, then the saturation flow is adjusted accordingly. But determination of saturation flow is a bit complex when shared lane operations are involved. In shared lane operations, there can be two conditions. One, that this lane is shared by right turning movement as well as through traffic, but when right turn moves, there is no opposing flow here. These vehicles are stopped. Means this is exclusive phase in the signal. Now in that case, for unopposed streams in individual lane, S1 is given by this equation. Now here dn is 1 for near side and 0 for non-near side lane. Small f is the proportion of turning traffic in the lane, g is the gradient, and r is the radius of the curve. Radius of the curve for right turning traffic. Now S0 here is given by this equation: 2080 minus 42 dg into g plus 100 into w minus 3 point. Now this is the adjustment for lane width, 100 PCU per meter lane width, and dg is 1 for uphill gradient and 0 for downhill gradient, and g is the gradient in percent. So using this equation you can calculate what is S0, and then putting in this equation you can find out what is the saturation flow for unopposed streams in individual lane. For opposed streams in individual lane means when the right turners move through opposing stream, so they will find some gap in the opposing stream. So for initial period of the green, these vehicles will not be able to move, and therefore you have to provide some storage space here so that these right turners can stand here without blocking the through traffic in this lane. And this is given by this equation: S2 is equal to Sg plus Sc. Sg is S0 minus 230 upon 1 plus small f into t minus 1, where t is through car unit factor for a turning vehicle. The saturation flow is always expressed in terms of through going vehicles, and each right turning vehicle is converted into equivalent number of through going vehicle. This is the t. Now f is the proportion of turning traffic. S0 I explained earlier. and the second term here SC is given by this equation, where this P is given by 1 plus summation of alpha into R1 into Pi, that is basically equivalent flow in PCU per hour. Alpha I is the PCU factor for a vehicle type I, and Pi is the proportion of that particular vehicle. NS is the number of right turning vehicle that can wait in the intersection area without blocking the through vehicle. I told you these vehicles will stay here till the queue from opposing stream has exhausted. So they should not block the through traffic in this lane. So how many storage spaces are available? That is NS. And X0 is the volume capacity ratio. That is S into G upon Q into C. Now take a small example that following data are collected at an approach to a signal control intersection. And what is this saturation flow? It is near side lane width is 2.4 meter, uphill gradient of 5%, radius of turn for right turning vehicle is 20 meter, and proportion right turning vehicle in the lane is 25%. So this is the first case. Okay, so we calculate S1 by this equation, S0 is given by this equation. Now here DG is 1 because it's a 5% uphill gradient, and G is 5%, W is 2.4 meter. So you can calculate S0 as 1785. You put this value here. Now DN is 1 for near side lane, and F is 25%, R is 20 meter. So you calculate S1 here, and that will be 1615 vehicles per hour of green. That is how the saturation flow is estimated using UK method. US method of estimating capacity of a signal control intersection is very comprehensive, and it starts with a simple method or a simple step to find out the rate of discharge under most ideal conditions, and that is called S0. S0 here is base saturation flow, and this base value is adjusted for a number of factors which are present at site. Now the SCM method is different from UK method in the sense that here the method is based on lane groups. It is not based on individual lane. So all lanes in the approach are divided into 3 lane groups. One lane is for straight going vehicles, another for left turners, another for right turners. Even if there are 5 lanes in the approach, they should be put into 3 lane groups depending upon the traffic operation. S0 is base saturation flow for a lane group per lane. N is the number of lanes in the lane group, and these are the adjustment factors. FW for lane width, FSV for heavy vehicle, for gradient, for type of area, for parking, for blocking effect of local buses, for lane utilization, for left turn, for right turn, and for pedestrian left turn and for pedestrian right turn. All these factors are to be estimated to get the actual value of S under prevailing roadway, traffic and signal conditions. Now majority of these factors are given in simple equation form. For example, FW, adjustment factor for lane width, is given by this equation where W is in feet. 12 feet is taken as standard lane width, and if it is not 12 meter, then it should be adjusted. For gradient, for heavy vehicle, where ET is the equivalency factor for heavy vehicle. In HCM, its value is suggested as 2, and this is percentage of heavy vehicle in the approach. For parking, adjustment factor for parking is given by this equation, where N is the number of lanes in the lane group and NM is the number of parking maneuvers per hour. Adjustment for local buses is given by this equation. Here NB is the number of buses stopping per hour. FLU, lane utilization factor, small FLU, is given by this equation, VG upon VG1, where VG is unadjusted demand flow rate for lane group and VG1 is unadjusted demand flow rate on single lane with highest volume in the lane group. So how flow is distributed different lanes. How the flow is distributed among the lanes, that is utilization factor. Now the adjustment factor for left turn and right turn are very complex. A turn can be made under 8 different conditions. 2 cases of geometry. Turn can be from exclusive lane or it can be from a shared lane. And 3 cases of signal. Turn during a protected phase, turn during a permitted phase, and turn during permitted plus protected phase. Now these 2 cases of geometry and 3 cases of signal will give you 6 different combinations. Now 2 special cases are added here. One, when you have a single lane approach, and when you have double exclusive turning lane. Now single lane approach is special because all 3 movements will be sharing the same lane, and double exclusive turning lane is also special because that indicates a very heavy turning traffic, and effect of more than one turning lane is different from effect of a single turning lane. So total 8 cases, and all these cases are discussed in the manual in detail. Now the last factor is pedestrian bicycle blockage factor, PLPB, pedestrian or bicycle, and these are given by this equation for left turn and for right turn, where this is proportion of left turning vehicle and this is the proportion of right turning vehicle, and APBT is given by this equation, volume of pedestrian divided by 2000, and F. Now F can be 0.6 or 1.0. It is 0.6 when number of cross street receiving lanes is more than number of turning lanes, otherwise it is 1 when they are equal. The third method is the Indo-highway capacity manual method. This method is relatively simpler. Now here S is given by this equation, S0 into W into FBB into FBR into FIS, where S0 depends upon the approach width. Here we do not consider the lane width. It is 630 per meter width, and that's why W is the width of the approach. So 630 for W less than 7 meter, 1140 minus 60W if the width of the approach is between 7 and 10.5 meter, and if it is more than 10.5 meter it is 500. W is the effective width of approach in meter used by the moment group, and these are 3 adjustment factors to this S value. This is the adjustment factor for bus blockage due to curbside bus stop. This is adjustment factor for blockage of through vehicles by standing right turning vehicles waiting for their turn, and FIS is a new factor which is introduced in Indo-HCM, that is the adjustment factor for initial surge of vehicles due to approach flare and anticipated effect. Now this is particularly important when you have high proportion of two-wheelers, that what happens practically if you see intersection, all these two-wheelers come at the stop line through zigzag movement in the approach, and they start moving immediately after onset of the green. Now that is initial surge. This is to be estimated. An adjustment factor for effect of local buses stopping the intersection is given by this equation, W minus 3 into TB into NB upon 3600 divided by W. Now here TB is the average blockage time during green, and NB is the number of local buses stopping in 1 hour. And if this value is more than 200, the SCM suggests that take the higher maximum value of NB as 200. FBR is given by this equation, where W is the width of the approach and this WR is the width of approach in meter along the median which is occupied by the standing vehicle waiting for the right turn phase. and this is to be applied only when there is no exclusive right turn phase provided to the right turning vehicle. Adjustment factor for initial surge is applied when flare effect or anticipated effect is observed at the intersection, and it depends upon the green time and the surge ratio. Now, surge ratio is the ratio of initial higher discharge rate due to either flare effect or anticipation effect or both to the uniform saturation flow. Now, anticipation effect basically means that, as I told you, motorized two-wheelers, they come at a stop line and they anticipate the change in the signal from red to green, and they start moving just before start of the green phase. That is anticipation effect, and therefore this table is given in the manual to calculate this value of FIS, that is the surge effect. If the green time phase is in this range, and if you have only anticipation effect, means there is no flare in the approach, then these are the values to be taken for FIS. And if this surge ratio is low or high and you have the only approach flare effect, and when you have both anticipation effect as well as approach flare effect, you can appropriately choose value of FIS. So friends, these are three methods of estimating saturation flow. You can write your feedback in the comment box. Thank you very much.